Hi, my name is Aldo Vicente. In this Redshift tutorial, we'll be talking about the Irradiance Cache GI engine. We'll start with a quick overview of how Irradiance Cache works and a look at its basic pros and cons. Then we'll open up our demo scene and break down what happens at render time with Irradiance Cache. And after that, we'll jump into the GI tab and go through all the features and parameters available for tweaking and optimizing it in our scene. So let's get started. Okay, so let's start by opening up our demo scene here. We have an environment dome and some portal lights lighting this small interior. Without any GI turned on, we get this pretty dark image because we're only going to be getting direct lighting. So let's take a look at that. So there it is. We can see there's zero bounce lighting, which is to be expected. So we're going to jump over to our render globals, and we're going to go over to our GI tab here. And for our primary engine, we're going to set it to Irradiance Cache. And let's take a quick render with the default settings. Save that. Okay, so we can see here that there's a big difference visually with almost no hit to render time, 2 seconds, but now we're actually getting bounce light. So if I run this render again, the first thing we notice when we render with Irradiance Cache is this pre-pass that's happening before the actual render begins. This is the Irradiance Cache Computation Path. And two things are happening during this pass. The first is the engine is deciding where in the frame to place the calculation points, and the second is it's actually calculating those points. So that once the next pass begins, the actual final render pass, it can use that data to fill in the Irradiance Cache values for all the other points in between. Like we talked about in the overview, Irradiance caching calculates point A and point E and then grades between them to approximate point B, C, and D. So that's what's happening here throughout the entire frame. So the computation pass is where the bulk of the Irradiance cache work actually takes place. One thing that's great about it is that once we've calculated that pass, we can save the data and actually reuse it to cut time on our next render. And that's actually what the first parameter controls in the Irradiance cache settings. So back here in our GI tab, if we look at the first parameter here in the Irradiance caching dropdown, it's mode. Currently it's set to rebuild don't save, which does just that. It will run the computation pass and it will build the Irradiance cache data, but it won't save it. So we can't reuse the pass that we just calculated, but that's okay. We can see that this next mode is rebuild pre-pass only. What this does is it will run the computation pass to determine and calculate our irradiance points, and once that pass is done, instead of moving on to the actual final render, it'll just stop like this. Pre-pass, save that. So we see the computation pass going, and typically as soon as that computation pass is done, it just jumps right into the final render. But again, when we have rebuild pre-pass only, it just stops. However, this time it actually will save the data from the calculation pass. We can see that when we switch to this mode, this file name parameter opened up, and this is just a path and a file name where we want this data to be stored. So the next mode is rebuild mode, and this does the same thing in that it also saves the Irradiance data from the computation pass, but the difference being that in rebuild mode, it actually goes on to render the final image like this. So we're going to save. There's our computation pass, and computation pass is done, and now the final image is rendering. So that is rebuild mode. Now the final mode is load mode. And we can see that the file name parameter here is still open. But in this mode, instead of saving data into this file, the engine is going to be loading data from this file. And since we're providing it all the Irradiance data already, this means that it doesn't need to run that computation pass again. It'll just load up the Irradiance data that we already saved and jump right into the final render pass, saving us some time as you can see here. So if I were to save this, you can see our previous render time with the rebuild mode was 16 seconds. Now that we're loading that data again and we hit render, you can see that it shouldn't go, see it's not doing the computation pass, it's just jumping straight into the render, and that should cut a couple seconds off of our time. So if we compare the two, 12 seconds, 16 seconds, and they look identical. Now, of course, if we move or change anything in our scene, some geo or a camera or anything like that, that would affect the irradiance data. Also, light intensities, moving lights around or changing material properties that affect how light bounces around. All of that would affect our irradiance paths and our irradiance data. So we would want to switch back to rebuild mode and run that computation path again. Okay, so moving on, here we see a parameter called fly through mode. It's grayed out right now, and that's because we're in load mode. But if we switch over to rebuild mode, you'll see it is active again. So let's go ahead and turn it on. So this is specifically for camera fly-through animations. So like we talked about earlier, part of the computation pass is the engine deciding where in frame to place all those computation points and deciding how to distribute them. In a camera fly-through animation where nothing is moving around in the scene, just the camera, a lot of those calculation points from one frame will still be usable in the next frame. So instead of completely redistributing these points for every single frame, this mode lets us recycle the calculated points created in the previous frame to use in the current frame. So since we already calculated the points from frame 1, now if we jump over to frame 2 and enable fly-through mode, with fly-through mode enabled already, we're telling Redshift to reuse those points that we already generated wherever possible to save us a bit of render time. So you can see that from frame 1 to frame 2 the camera moves very slightly. Let me switch over the render cam. It just moves a little bit forward. So let's run our test render real quick. We're going to save that. Okay, so here's our render, 14 seconds. Now let's quickly disable fly-through mode to see how long it would have taken without reusing the points from frame 1. So we'll save and do another render. Skip ahead real quick. Okay, so 15 seconds, 1 second difference, not a huge deal. But with higher resolutions and more detail in the frames, over the course of say a 900 frame animation, for instance, this can be a pretty significant time saver. Okay, so our next parameter is number of frames to blend. This is grayed out currently because it can only be used in load mode, so we'll switch over. So this is another parameter that's specific to animations. One potential problem with Irradiance Cache mode is flickering during animation due to insufficient quality settings or difficult lighting situations. So this parameter is designed to help reduce the flickering from frame to frame by basically averaging the results of multiple Irradiance Cache files. And of course this is only available in load mode because we would need to have these cache files saved out already in order to be able to average them together. Okay, so next up is show calculation. This is checked on automatically, and it's just to let us see the computation path as it is being calculated. Basically, what we see here, if we switch to rebuild mode, when show calculation is enabled, we get to see this pass happening. So I'm going to go ahead and cancel this render. Now, if I were to disable show calculation, it would still run that computation path, but it won't show it to us. It will be happening here in the background. You can see the loading bar here. And once it's done, it just resumes the final render like normal. And there it is. So next up, we have use separate points for secondary rays. So sometimes when we're using Irradiance Cache in a scene with blurry reflections and refractions with high sample rates, some flickering might occur. So what this setting does is it will store points from reflection and refraction rays, which are secondary points. It'll store those separately from primary camera ray points, like Irradiance Cache points are. So generally that'll help resolve that flickering issue. Of course, since we're storing these separately now, it will have a small effect on render time and storage, but honestly it doesn't come into play too often. So that's a good look at the basics of the Irradiance Cache computation paths. In the next video, we'll start breaking down each of the optimization parameters we see down here. So in this video, we'll be breaking down each of the optimization parameters for Irradiance Cache, starting with probably my favorite feature in this entire tab, and that is this Visualize Points feature. So this is a diagnostics feature that will actually render out the Irradiance points so that we know exactly where they're being placed throughout our frame. So if we enable it real quick and set up a render, okay, so there they are. We should note that when this feature is enabled, we don't actually get the GI effect itself, just the points and of course the direct light that we have coming from these portal lights. So as mentioned earlier, part of what is happening during the Irradiance Cache computation pass is Redshift is determining where to put these calculation points. And this is a really important part of the optimization process because of course every point gives us a cleaner, more accurate result, but adds to our calculation time. So we want to make sure that we're not wasting irradiance points in areas that don't really need them, while at the same time we want to make sure that we do have enough point density in areas that do need them. So typically large flat areas need less points, but corners and areas with a lot of color detail or lighting detail will need more calculation points in order to stay accurate. And we can see the engine is already doing that here. Our point densities are more heavy around corners and around contact areas than they are around, like, you know, the flat ground or the flat wall here. And a lot of the remaining parameters here are there to help us tweak and optimize this distribution. And the Visualize Points feature here will make it easier for us to understand how these parameters affect our point densities. So we'll leave this enabled for now. Let's check out our next set of parameters. First, we have this preset dropdown that lets us choose between custom, low, medium, and high. Obviously, these are quality presets. If we set it to high, for instance, we can see that it's going to adjust and gray out everything from min rate down to radius factor. So let's switch back to custom and break down how each of these settings work. These are kind of similar to other adaptive sampling controls at render time during our Irradiance cache computation pass. The first thing Redshift will do is it's going to shoot a certain number of rays out from the camera into our scene. These rays are going to create sort of our first pass of Irradiance cache points. Now, the first set of points are all evenly spaced out, and they're basically cast out in kind of a uniform pattern across our frame, and they look something like this. If we were to lock both min and max rate to -4, for instance. So they look sort of like this. You can see initially there's no real consideration for corners or changes in lighting or directionality. They're pretty much all evenly spaced apart. Now, how close together or far apart these points are cast is based on our min rate value. In this example, obviously, we have it at -4, and I just set the max rate value to -4 to lock it into that min rate value. And here's what it would look like if our min rate value was -3. So now they're more dense and more close together compared to when they were at -4. If they were at, you know, -2 or -1, they'd be even more close together. And if we were to set this min rate value to 0, we would basically have 1 point for every single pixel in our frame. So we can pretty much tell that these rate values refer to subdivisions. So a min rate, for example, of -1 would give us a point density of 1 point for every 4 pixels. A min rate of -2 would give us 1 point for every 16 pixels, and so on like that. Generally, -3 is a good minimum rate, and that of course gives us an initial pass of 1 point for every 64 pixels like we see here. Okay, so what happens next in the computation pass? Well, once it has laid out this first pass of irradiance points, Redshift will take 3 measurements from each point, and it will use those measurements to determine whether or not more points are needed for any particular area. These 3 measurements are color, distance, and the surface normal. and they correspond to our 3 threshold parameters down here. So let's talk about the color threshold. Basically, when Redshift measures the color of a certain point, it's going to compare it to the color of the points around it to determine how much they contrast from each other. If the contrast between them is higher than this color threshold value, then Redshift will say this needs more points and it'll add more points into that area. Therefore, a lower threshold is going to result typically in more points, whereas a higher threshold is going to result, of course, in less points. Typically, somewhere between 0.01 and 0.001 works pretty well. Okay, so next is our distance threshold. So as mentioned earlier, GUI values can change pretty drastically near corners and creases. So for each initial point cast, Redshift is going to measure the distance from that point to the nearest object or objects. If there is other geo within a certain distance, which is our distance threshold, then Redshift will add more points to help with that calculation. So we can see that our distance threshold doesn't actually have a number input like occlusion distance, for example. Instead, it has a drop down with very low, low, medium, and high settings. So at first, I thought this was referring to low threshold versus high threshold. So I thought a low threshold would result in more points, but actually the opposite is true. This is actually a quality setting. So high settings are going to result in more points, and low settings are going to result in less points. And we can verify that by doing 2 quick comparison renders with low and high thresholds. So if we set our distance threshold to low and let's set our max rate to 0 for the time being, we'll run a test render with that. So we can see some points around our corners and contact areas, like here and here and here. Now let's see how that changes when we switch to high quality distance threshold. We'll save that and run one more test render. Okay, so we can see a pretty big difference if we switch back and forth between the two. We have a lot more points in the corners and in the contact areas, especially along this wall here. So obviously, having all these extra points would mean we get more accurate GI in areas with a lot of physical detail, but of course, more points also means more calculation time. Generally speaking, medium setting will work just fine for almost all cases. Alright, let's move on to the normal threshold. So again, as mentioned earlier, GI values can change pretty dramatically over curved surfaces. So to account for this, Redshift will measure the surface normal of each point and then compare it to the normals of the points around it. And again, if the difference is above the normal threshold, that means the surface is curving too much and will require more points. So similar to the distance threshold, this normal threshold, instead of being a value, it's just another quality setting. So here we have low, medium, and high, and it's the same concept. You know, a low quality setting will result in less points, faster but less accurate, and a high quality setting will result in more points, which is more accurate, but will take a little more computation time. Again, let's run a quick comparison of low to high settings. So we'll start with low, save this and do a test render. Okay, so there is our low quality normal threshold. We can see that there isn't a ton of extra density around the curved surfaces of the spheres compared to the ground. It looks like they're actually pretty much about the same density for the most part. Now let's do a test render with the high quality normal threshold. So we'll save this, we'll do one more render. Okay, so there is our high quality normal threshold. We can see the point density on the flat surfaces like the floor and the wall have stayed pretty much exactly the same if we flip back and forth between the two. But at the same time, we can see that the point density on the curved surface of the spheres has increased dramatically between the low setting and the high setting. And again, this is because as the surface normal changes, the GI values will change too. So Redshift will want to allocate more points to more accurately calculate that shift. Okay, so those are the 3 threshold settings that Redshift uses to determine whether or not to add more points after the initial pass. So, quick recap. First thing that happens in the Irradiance Cache Computation Path is Redshift will uniformly cast points across our frame using the min rate to determine that pattern's density. And that first part looks something like this. So once it has this initial uniform pass, it's going to measure the color distance and the surface normals of each of those points to determine where more points are needed, and it's going to use these threshold values to determine if they are too high or too low. If the point density in certain areas is too low, it will add more points to those areas by going up one subdivision like this. So what happens next? Well, then it repeats the process and measures color, distance, and normals for these new points, and again adds one subdivision of points wherever necessary, and that looks like this. And it's going to continue to repeat this process of measuring and adding points until it's reached our max rate. So this max rate, of course, is how Redshift knows to stop adding more points regardless of measurements or threshold values. And again, these are subdivision values, so a max rate of 0 means there will be no subdivision. So for every 1 pixel, there will be 1 point. And a max rate of 1, for instance, would mean to subdivide once, so there would be 4 points for every 1 pixel, and so on. Typically, a max rate of 0 works pretty well in most cases. If we have really high detail in a certain area, we may want to go up to 1, but 0 works pretty well for most cases. So that's pretty much it for this section. In the next video, we'll be breaking down the min detail and radius factor.